there is no
battery.
So if it doesn't work,
yeah, please.
There is a stick.
There is a stick here. That's. There is a stick or no?
Yeah, there was a stick.
There was.
Everything is disappearing probably. Well, anyway.
Okay. Yeah.
Okay. So we are going to have Hamid from the university to tell us about testing correlation.
Thanks for inviting me here. I'll talk about some general ideas in this first. So when we talk about structures and functions, we might, so the first thing that comes to mind is this very structure, this very strong form of the statement that the structure of the function can be described very easily. For example, a rank 1 matrix or a low degree polynomial is a very structured object. And there is this weak sense of it which says that the structure is somewhere hidden. There is some weak form of structure in our object. So this is usually captured by this correlation with the structured function. For example, if the matrix is correlated with a rank 1 matrix, or if our function is correlated with a low degree polynomial, we can say that there is this weak structure somewhere inside the function. And the usual theme in property testing is to study this strong form. So it's that given a function, we want to see if it has this structure, this strong form of structure. But here we'll focus on the second form. So we are interested in detecting that whether a function has this weak form of structure. Now, so the question in a very vague and imprecise form is this, that we are going to study, that which weak forms are actually testable. So what is testing? So a function f is given. We are allowed to read the value of f on only a few random points, from which the randomness comes from the distribution that we pick. And then according to which we want to see whether f has this weak structure or not. Now, a central tool here is the uniformity norms. Let me start by defining them. They are defined in different contexts, and they're supposed to distinguish typical random functions from certain structured functions. And the way that they distinguish is that it's because a typical random function has a small uniformity norm, while if your function has large uniformity norm, then it has this weak structure. So it correlates with something very structured. Like again, rank 1 matrix or a low degree polynomial or a constant step nil system. Now, the setting of this stack will be, so as I said, these are defined in different contexts. But in this stack, we are interested only in fp to the n. So p is a fixed prime, and we study functions from fp to the n to complex numbers. And we consider this space as a Hilbert space with the inner product, which is defined as the expected value of f of x times conjugate of g. So we take the average when we take the dot product. Okay. So let me define the uniformity norms in this context. So we have a function from fp to the n to c. Then the UK norm of f, the kth Gowers norm of f, is defined the following way. If we raise it to power 2 to the k, then we'll get this expected value, which is we have this product which runs over all subsets of k. And for each subset, we add x to this sum of yi's which are in S. And this C is the complex conjugation. So if the size of S is odd, we conjugate this term. And these x, y1 to yk are IID random variables taking uniform values in fp to the n. So that's the definition of the UK norm in this context. So for example, U2 norm will be the following. So k is 2. We have subsets. So y1, y2, y1, y2, all the subsets. And for this one, the empty set. If the size is odd, we conjugate it. So here we have only one y. Here we have only one y, so we conjugate. And similarly, the U3 norm.
Dr. Ash, I mean, first of all, I'm sure maybe most people have seen it, but you will put a picture of a parallelogram, or just for people who haven't seen it, right? So,
yeah, okay.
I mean, what are these? It's a very simple structure. The things you are averaging the values. So you want to draw it, or you want to say?
So we can consider this subset of S as vertices of a parallelogram, and so no, I don't. So yeah, okay. So I'm not going to actually use the formula of this thing, but this is given by the formula, and the only thing that I'm interested in here is that it is given by these linear forms, this linear combination of these random variables. Okay, so
for the case norm, you pick 2 to the k points at random, which are like a subspace or a subcube.
Subcube.
And you multiply all the values of the.
Yeah, so you pick one x and you pick k different directions. So, and for each direction you continue and you get a parallelogram, and you multiply the value of f on the vertices of this parallelogram, and you conjugate certain ones.
We probably can think of real values and forget.
Yeah, that complex.
If we want. So this is a minor issue. So you just multiply all the 2 to the k values function and take the 2 to the k root, so it makes sense, and then you have it.
Yeah, so it's not difficult to see that actually this formula that we get, this expected value is always a non-negative real number, and again, it's not trivial, but also not very difficult to prove that it satisfies the triangle inequality. So this is actually a norm. Now, what is the relation to property testing? So we have this formula for u to the k, for uk norm when the function is real. So we'll focus on functions which take only -1 and 1 value. So we have a function f from fp to the n to -1, 1. Now, it is possible to estimate these uniformity norms empirically. And what do exactly I mean by that? We pick some constant n, it's a large constant, and then we pick empirical samples for these random variables x and yi. So we pick for every j between 1 and n, we pick a sample of these uniformly at random. Now, when you have these samples, you can estimate the expected value of using them. So we estimate it with this expected value over all these j's between 1 and n and these products. Now, a simple second moment argument shows that if you take n to be sufficiently large, you get a good estimate of these uniformity norms. So in the context of property testing, you can estimate these norms. Now, but what information do we gain from these estimates? So this kind of information, they're given by these direct inverse theorems. For example, let's look at the simplest case where k is equal to 2, so the u2 norm. In this case, it's a well-known fact that if this norm is large, if and only if your function correlates with a character. So this is an if and only if statement. So you can, and this is the kind of weak structure that we were interested. So if you can estimate this norm, you'd be able to tell whether your function has a large correlation with a character or not. So let me write exactly what is this statement. So it has two directions. One is, I call it a direct theorem, which says that if you have correlation, if your function f correlates with a character, so if the correlation is at least delta, then the u2 norm is at least delta. And there is the inverse theorem, which says that the opposite is also true, but with different parameters. So if your u2 norm is large, if it's larger than some constant delta, then there is a character such that your function, the correlation of your function with it is at least square root delta.
Are these best possible?
Yes.
Yeah. Let me add another comment for those don't recognize it in this form. This is just a linearity testing of so character, just a linear function over this group, and this is just testing the u2 norm is exactly doing the linearity test of Lamont, Robinson, and PLR.
Yeah. Now let us, so this gives a way to correlate, to test correlation with characters. Now we want to define some general framework to be able to formulate these kind of statements. Now, we have a set Dn of which we think of them as structured functions on fp to the n, similar to characters. We want to define uniformity with respect to this set Dn. So for a function f from fp to the n to complex numbers, we define the uniformity norm of f with respect to this set Dn to be the supremum of this correlation of f with elements of G. So this is trivially a semi-norm and will require some conditions to make it actually a norm, some trivial conditions. So we call it the uniformity with respect to Dn. And if we want to rephrase the inverse theorem from the previous slide using this new notation, it says that if the U2 norm is at least delta, then the uniformity with respect to characters of f is at least a square root delta. Now, I'll use this notation omega sub p to denote e to the 2 pi I over p, because I'm going to do some Fourier analysis. And now let this p sub d of n denote the set of all these omega p to some polynomial px, where p is of degree at most d. So you take this set of all polynomials of degree, multivariable polynomials of degree at most d over fp, and you raise this omega p to the power of p. Now, recently, when the characteristic of the field is sufficiently large, so it generalizes the theorem that I had in the previous slides about the U2 norm. So the theorem says that if d is some number which is less than p, so p must be larger than d, then there is some function delta such that for every bounded function, so f goes from fp to the n to this interval minus 1, 1, and every epsilon at least 0, if your function is uniform if it's non-uniform with respect to these polynomials, so if it has some correlation with one of these omega p2 powers of the polynomial, then the uniformity norm, the d plus 1th uniformity norm of f is large. So this is the easy direction. It was known before.
A special case of this is the epsilon equals 1. If your function is
exactly one of them.
Polynomial, then it would be
exactly 1, yes. So
was that theorem ready for the f going to minus 1, 1?
Okay. So this part is for general, but the second part, the inverse theorem, which requires that. So the second part says that if the uniformity norm is large, then you correlate with some polynomial of degree at most d. So the uniformity norm of f with respect to these omega p2 polynomials of degree d is at least some constant which depends on epsilon, but it bounded away from 0.
Is it important that the function takes only real values?
No. No, it works for complex values too. But yeah, so the point is that delta doesn't depend on n, so it's just a function of epsilon. Now, in general, we have a fixed p, and we are interested in asymptotic behavior of things as n goes to infinity. So instead of one set dn, let me define a sequence of these sets. So let this calligraphic d be a sequence of these dn's, where dn's are as before. So they are functions from fp to the n to c. And I'll use, for every function from fp to the n to c, I'll use this ud to denote the previous udn. So we pick the value of n as the dimension of the domain of f, and we define the norm with respect to this family, this sequence of families to be uniformity with respect to dn. Now, let me rephrase the question that I'm interested in a bit more precise way, again, not completely rigorous. Now, we want to see for which families d, for every fixed epsilon, there is a test that distinguishes between functions from fp to the n to minus 1, 1 that are non-uniform, so their uniformity norm is at least epsilon, from the functions that are uniform. So their uniformity norm is at most some delta, which is a positive number depending on epsilon. So we are able to distinguish between the case where the uniformity which is non-uniform, so the uniformity norm is large, from the one that the uniformity norm is small. So we know that we can do it for polynomials because of the theorem of Bergeson, Tao, and Ziegler. And the question is that for which other families we are able to do this. So we need to require some conditions on D. So at this present form that I stated the question, we are treating fp to the n as a generic set of size p to the n. We are not using anything about the algebraic structure of fp to the n. So we totally ignored the algebraic structure of fp to the n. So we
it's not clear because the tests that the uniformity norms prescribe are tests of the parity checks of polynomials, right? That's what they are testing.
No, but I defined this testing question for a general D. So, I mean, in the previous slide. I didn't have any condition on D.
Yeah,
So
I don't know what it means that we've treated so far.
So-
we had
On the last slide.
on the last slide,
oh,
yes,
last
yes.
slide, so far it's just on the
Yeah, on the last slide. Yeah, so because the Hilbert structure is just the average over all the points of fp to the n. So what conditions should we require from this norm? We want it to be invariant under affine transformations, under invertible affine transformation. So if you pick any c in fp to the n and any function f, if you shift the function by that c, we don't want this norm to change. So we want it to satisfy this. And also, we want it to be invariant under invertible linear transformation. So if you take an n by n invertible matrix and you act it on f, we don't want the norm to change. So this takes care of all the algebraic symmetries of fp to the n.
So that's the framework of Kaufman and Sudan, basically. The framework of invariant
Under affine transformation, yes. And we'll also require that these dn and dm's to be consistent. This is more of a convenient condition, which is not that crucial. But it will make our results to look neater and easier to state. So what do I exactly mean by this? If you take this function from fp to the n to c, which takes this vector and maps it to omega p to x1, we want to have the same norm as this function treated as some function from fp to the m to c. So this function we want just treat it as a single function when we're computing its norm. We want to forget that in which domain it is stated. So let me formalize this. So for every m larger than n, there is a natural projection from fp to the m to fp to the n by just dropping the last coordinates. And I want the norm to satisfy the following property. If you take a function from fp to the n to c, and if you treat it as a function from fp to the m to c, so if you compose it with the projection, you want to have the same norms. And so let me state.
Sorry, for which projections? For just the fixed projection?
Yeah, the one that drops the last coordinates.
The invariance of the affine invariance, so it doesn't.
Yeah, it doesn't actually. So I'll call a family of these dn's an invariant norming family if for every invertible affine transformation, if G belongs to my set, then also this affine transformation of G also belongs to my set. And I'll also require this condition, which is maybe not so natural, but without it I will not be able to prove anything. So I require these functions to be bounded. So the L infinity norm of each one is at most 1, similar to characters or is omega p to polynomials. And I require that for every g, so if you take one g in dn, then composition with these projections also belong to the space dm, and this is an if and only if statement. So these are consistent. And also, again, a very natural condition, which is just again for the sake of convenience, is that dn spans all of L2 to all the space of functions on fp to the n. This is to make the uniformity norm to be actually a norm. But without it, we can restrict to subspaces, so it's not such an important condition. And if you require these conditions on a norming family, then the norm that is defined, it will actually be a norm, not just a semi-norm because of the last condition. And it will be invariant under this affine transformation. And again, it will be consistent with these projections. Now, let me restate the question that I'm interested in, again, in a more precise but not completely rigid. So I want to see for which invariant norming families there is this test that distinguishes the non-uniform case from the uniform case. So the only part that is missing at this point is this test part. So I haven't defined it rigorously. So to define it, let me define some notation first. So for us, a linear form L in k variables is just a vector in fp to the k. So it's some lambda 1 lambda k in fp to the k. So each one is an element of fp to the k. And we treat this vector as a vector of coefficients. So L is a function from fp to the n to fp to the n to k to fp to the n in the following way. If you take a vector x in fp to the n to k, so each one of these x1 to xk is itself a vector in fp to the n. It's a point in our space. Then L of x is just the linear combination of these with the coefficients that come from the linear form. So it's just a set of coefficients. We call them linear forms. And we'll use the term system of linear forms to refer to these sets of linear forms in k variables. Now, consider a system of linear forms L1 to Lm and a function from fp to the n to c. We define the average TL of f to be the following. So it's the expected value of, so we take this product I goes from 1 to m, and we look at the f of Li of this vector x. And x is a uniform random variable in this space. So we pick these x's uniformly at random. We look at the value of the linear form over them. We take the product and the expected value.
No conjugates?
No, because it's the, oh, OK, I defined to see. No, but yeah, I don't need it, actually.
So
Yeah.
you want to say that the special case of this is a uniformity
Norm under
k plus
under real numbers, yes. Yeah, so in this talk, I'm mainly interested in real numbers. So I'm not going to use
No, but the special case of this very general definition are all the uniformity
norms, yeah.
M is 2 to the k, and you have, I guess,
That's
k
the
plus one,
example
but
he just
Yeah, this is the example. Yeah, so if you take f to be a function from fp to the n to r, and if you let the coefficients, your set of linear forms to be this, then the average t sub L of f will be the following. It will be the expected value of these products. So in the first one, you'll have just x1 because you have 1 for just the first one and 0 for the other two variables. In the second one, you get x1 plus x2 because of those two 1s and the 0 in the third. And so you get this product of 4 terms, which is just the uniformity U2 norm of f to power raised to power 4 because f is a real valued function. So let me also give another example. Now, consider a subset of fp to the n, A, and let's look at these three linear forms. Then TL of the indicator function of A will be, f should be this 1 over A. It's, so f is just the indicator function of A, then f of x1 plus x2, f of x1 plus 2x2. So this average counts, gives us the density of 3-term arithmetic progressions inside the subset A. So these averages are very common when you count the number of times that a linear pattern appears in a subset. Now, I'll call a family of linear forms homogeneous if they all start with coefficient 1. So it looks a bit technical, but I'm going to use it later. So here, if you look at this 3-term arithmetic progression, each one starts with 1. So it's a homogeneous family of linear forms. Also, similarly for the Gowers norm.
So the first coordinate is always
Is,
1
yes. So
seems like a very structured form of test, basically the Gowers norm and generalizations. For property testing, okay, so when you have a test of this form, that's saying a lot, but a negative result saying you don't have a test of this form would at least seem not to be saying that the property's not testable, the norm's not testable.
Why it's not going to say?
Well, because you could have a, you know, you say like a more general class of tests, you'd just be allowed to query the function at any point, any small number of points, and use any algorithm based on the values of the function.
Yes. So I'm going, I haven't defined the test yet, but
Oh, okay.
yeah.
So this isn't the definition of
Not the test, no. It's just the average. So,
So can I ask?
Sure.
You use f on all the linear forms, the same f. Is that really necessary? In Gowers norm, you don't. Because it's a norm, you can. There's the case that if you have f1 to fk, then it's less than the product of
the
fi's when you,
yes.
when you Cauchy.
Yes, but I mean, for the Gowers norm, you use one f when you define the norm of an f. But you can use different f's. Then I mean, it's not.
It's the same here as where you're going or not.
No, I'm not going to use it. No. Now consider an invariant norming family D, a function f which takes only values -1 and 1, and a parameter epsilon greater than 0. Let's see what can we do by just reading the value of f on random points. So we can pick a k epsilon tuple, where k depends on epsilon, in fp to the n k. So we pick these k points according to some distribution that we like. So we picked. And then we read the value of these f on these points, and we guess whether the uniformity norm is large or it is less than some delta, which depends on epsilon.
When you say guess, you mean to look at all the variations of all functions in your family on this set and guess according to that?
No. We have a function f. We look at these values. There are only 2 to the k possibilities because it takes -1, 1. And according to each possibility, we are allowed to say that our function is non-uniform or it is uniform.
But the definition of non-uniformity is the maximum correlation.
Yes, but we don't know.
So when you say guess, you mean look?
No, we will give some answer according to these values. We'll say that it is uniform. And we want this answer to be correct probabilistically with some high probability.
An efficient procedure to give
Yes. So we don't want the guess to be something like a random guess. We want it to be better than random guess. So if this happens, then there's a good chance that we'll say the function is uniform.
In the case of polynomials, you evaluated some average, which was instead of guessing,
Yeah.
say the estimator. Yeah, but you
No, but
these norms are not like Gowers norms, right? I mean, these norms are complicated. It's a maximum correlation with some family.
Yeah, but
Yeah.
like, if the family is low degree polynomials, then Gowers norm gives you an algorithm to estimate.
Yeah.
Because of the inverse theorem. So you can ask where else.
No, but even the Gowers norm doesn't give us the estimate for the correlation to polynomials. Doesn't give us the exact estimate. It can tell us that it's either higher than this number or less than that number. So our family is invariant. So what happens if we replace f with some affine transformation with a random affine transformation of f? Then this won't change the value of the norm, so we should give the same answer. So this tells us that we can do the following instead. We can pick these k epsilon points according to the distribution, and then after that, we pick some matrix A, invertible matrix A, and some points C uniformly at random, and we evaluate the value of f on these points instead of just the points x1 to xc. So in other words, it tells us that there is no loss of generality if we assume that our distribution is invariant under this affine transformation, and according to which, again, we guess. Now, if you look at some fixed points, x1 to xk, then what is the distribution of ax1 plus c and to axk plus c, where a and c are random? This will be the distribution of some linear forms L1y, L2y to Lky, where y is a random variable, uniformly random variable. So these linear forms, they come from the linear structure of these points. So what we are doing here, after applying this random step, everything goes to the linear form setting. And since the number of linear forms is in k variables is finite, okay, so have this, and I'll make two more observations and then give the formal definition of testing. Now, consider a function f, some linear forms, and for every subset of M, let me define L sub s to be the linear forms whose indices are in S. Now, the distribution of f over these linear forms is determined by these averages, because f only takes values -1 and 1. So if you know all these averages for all the values of S, then you know what is the distribution of these f of L1 of x to Lk of x. So it's the average defined by this system of linear forms, as before.
The average of the product.
Yes, the average of the product.
Why is it related to -1, 1?
Because you can, yes. Well, in this setting, we are only working with the Boolean functions. But for any function, then, yeah, then I'll need coefficients, not just. And also, if you have a system of linear forms and the function from fp to the n to -1, 1, then you are able to estimate the value of this average empirically, the way that we did for the Gowers norm by just taking different samples. So we can estimate these things, and if we know these things, we know these distributions, which was what we had from the previous vague definition of testing. So let me give now a formal definition of what is correlation testable. We call an invariant norming family D correlation testable if for every parameter epsilon there is some delta, positive number delta, which depends on epsilon, it's positive, and some homogeneous systems of linear forms, L1 to k. So each one of these is a system of linear forms. It contains some linear forms, such that if you look at these two sets of points, so what is t? For each function, which is a function from fp to the n to -1, 1, and its uniformity norm is large, so it's non-uniform, we look at these averages of f. So this gives us a point, which I call it the profile of this function f. So we compute different averages for these f's, which are non-uniform. So we get a set of points in R to the k. And we do the same thing for the functions which are uniform. So they have low uniformity norm. And we get a different set S. We call it correlation, this family correlation testable if these two sets, if the closure of these two sets are disjoint. So this infimum is at greater than 0. The infimum is over the points inside T and inside S and their distance. So we have a set T for the functions which are uniform. We have a set S for the functions, T for non-uniform, S for uniform. If they are well separated, if their closure is disjoint, we can estimate these things with any error that we want, arbitrary error, and according to where they fall closer to T or S, we can distinguish between the case where f is the uniformity norm of f is at least epsilon, or the uniformity norm is at least delta.
So in the case of Gowers norms, this will be these different L's will be the.
There will be just one L.
There will be just one L.
Yes,
Yeah.
but
Yeah.
yeah. So for Gowers norms, you can, for correlation with polynomials, you can do it with just one average, and that's the average that comes from the Gowers norm. But if you want to be general, you have to allow these different linear forms. And a technical thing which comes from the fact that we cannot handle the low characteristic case yet, is that we call the system correlation testable of Gowers-Wolff complexity D if these linear forms, they satisfy some condition, which is that they are of Gowers-Wolff complexity at most D. I'm going to define it more formally. But we restrict to some special linear forms. OK, so finally, the main theorem that I'm going to show is the following. If you have a family of invariant norming family D, which is correlation testable, we wanted to characterize these things. And if its Gowers-Wolff complexity is at most D, which is less than P, so its characteristic of our field is large enough, P is large enough.
So sorry, this Gauss-Norm complexity is a complexity of D or complexity of the families that appear in the...
Of the families that appear. So each family of linear forms, they have some Gowers-Wolff complexity, and we want all of them to be of Gowers-Wolff complexity at most D.
This Gauss-Wolff complexity is between what? I mean, there's some...
It's always a constant which is bounded by the size of by the number of linear terms that appear in your formula.
That's only for correlation testable families. The Gauss-Norm complexity
is for every system of linear forms. It's defined for...
It's actual complexity of a linear form.
Of a system of linear forms.
What's the trivial upper bound again?
The size of the number of linear forms that we have. Yes. Yeah.
So is it just sort of what degree Gowers norm do you need to control the linear form, or is it something?
No, it's just that when the Gowers-Wolff complexity is small, you can remove, when you apply, I mean, I'm going to say exactly what it means after a few slides. But you can do approximations with using the inverse theorem that I said. But anyways, the theorem, so ignore this part actually, so it's very technical thing that we have to add. But the theorem says that if you have this linear form which is correlation testable, then there exists some constant, some k, which is at most D, such that your norm is equivalent to the Gowers norm in the following sense. That if you have a sequence of functions, their uniformity with respect to D goes to 0 if and only if the same thing happens with Gowers norm. So asymptotically, you are uniform with respect to family D if and only if you are uniform with respect to the UK norm. So you cannot do anything other than what Gowers norms give you.
What is Fn?
Fn is a sequence of functions which take only values -1 and 1.
So for any sequence of functions?
Yes. So for any sequence of functions, we have this equivalence. So basically tells that what we get from Gowers norms is everything. We cannot test anything else.
Why does this exist?
Because the uniformity, it doesn't tell us that exactly these are the all sets that we can test, but it tells us that if you are able to test something, then the notion of uniformity that comes from that test is the same notion of uniformity that comes from a Gowers norm. So you have to.
So is this correspondence also holding for the same n, or like you say for some n if the UD is large, then for some other n UK is larger, like if you want to...
No, it doesn't matter. So you can take any sequence.
No, he's asking how uniform in N are you? So suppose I give you just Fn for a fixed N. Which is very small.
Yeah, then you
in the U of D norm, then you will construct a function on much larger N.
No, it's the same N.
It's the same N.
Yeah,
So you don't need really this notation.
But then you have different epsilon.
Parameters epsilon,
Yeah.
but
Yes,
but
yes.
you stay within the same N.
Yes, it's the same.
So since I don't think you are going to mention Kaufman Sudan at all.
No.
You are not.
No.
So I just, for those who don't know, the whole framework of affine invariant testing was done for the unique decoding regime, basically distinguishing not epsilon and delta, but distinguishing 1 and 1 minus epsilon. And they also have a characterization of
Yes.
the situation, which is very different. It's a different game, but they also have a characterization of the stability.
Yeah, so,
So do you ever get k less than D?
yes. So yes, for example, this D can be just a U2 norm. I mean, the characters, for example, if you take characters. So D is just a bound on the Gowers-Wolff complexity of the linear forms. So it's
Right, but it's, I mean, my guess would be something like if you were to do some more general classes of F, then K would equal D. I mean, the Gowers-Wolff complexity is telling you something about how
the
often you have to Cauchy-Schwarz
yes.
linear forms. That's what it's sort of defined as. But the point is that you're restricting your...
No, but this depends, K depends on family D. So...
Well, if you want, you can write a weaker statement. Just put D instead of K on the right-hand side.
No, then... Oh, okay. No, then you won't have equivalence.
So, I mean,
you want to have equivalence.
Yes.
and the issue of the definition of the Gowers-Wolff complexity is it's a very precise number D. I mean, it can be treated as a bound, but
Oh,
it
okay.
has to be exactly the exactly right number of Cauchy-Schwarzes you have to do to go down to trivial.
Yes.
So that's why I think in a more general setting it should be exactly the right answer. I don't know what that setting is.
I mean, the problem is that this D appears only as a bound on the Cauchy-Schwarz complexity of these complexity of these linear forms. So you can add one linear form of some very high Gowers-Wolff complexity, but ignore it when you're finding the test. So this K will be actually the largest polynomial that you can find it inside D, correlates to some element of K. D.
So if you like interpret both sides, so one side is saying that a function has very low correlation with the elements of D. The other side is saying that the function has very low correlation with exponents of polynomials.
Yes.
So does that mean that the elements of D have very high correlation
with polynomials of...
polynomial?
Yes. So this K is the largest K such that you can find the polynomial of degree K that correlates with an element in D. Okay, so in a very vague sense, this statement can be interpreted as the statement that these uniformities that come from Gowers uniformity norms are the only possible uniformity norms. So when I was thinking about this question, I wasn't actually, I mean, when we started thinking, we weren't thinking about testing that much. We wanted to see if you can find some other notions of uniformity. Yes, I'll define a few more slides.
They
After.
call it true complexity.
Yeah, they call it true complexity. Which they call everything complexity, which the size of the decomposition, everything. The term appears many times. So, okay, I'm going to give a sketch of the proof, but first I will need to develop some tools. So, the main tool is, one of the main tools is higher degree Fourier analysis, and I'll say what this exactly means. Consider a constant C and a lambda in fp to the C. Then, if you look at the corresponding character of lambda, it is defined as this exponent of sum of lambda I xi's, where xi's are coordinate of x. So this is a polynomial of degree 1. So we can think of characters as these exponents of homogeneous polynomials of degree 1. So in higher degree Fourier analysis, the role of characters is played by these exponents of polynomials. So instead of just linear forms, these linear polynomials will be allow higher degree polynomials in the exponent. Now, let us denote the set of, so this slide was from previous case. So these exponents appeared when we talked about the inverse theorem. So remember that this PD was this set of exponents of polynomials of degree at most D. And we saw, we had this theorem of Bergelsen, Tau, and Ziegler, which was saying that if the uniformity norm of f is large, then it correlates with one of these polynomials. So it's, in a very standard way, it's possible to use this theorem to obtain a decomposition theorem, which says the following. Take a bounded function f, so it's from fp to the n to -1, 1. Then there exists some c which depends on d, some parameter, and delta again, another parameter. So it doesn't depend on n. And then you have these polynomials of p1 to pc. So their number is just a function of d and delta. And they are of degree at most d. And you can decompose f in the following way. You can write it as a function of these polynomials plus some error term h. So the first part is just a function of this constant number of polynomials, p1 of x, p2 pc of x. And there is this h part. Now, the h part, it's like a random noise, or it's a very uniform part. It's ud plus 1 norm is bounded by delta. If you take delta to be small, that will be very uniform. And the first part is also keeps the boundedness. So its L infinity norm is 1. Now, if we write the Fourier expansion of this f, we'll get the following formula. So for every lambda in fp to the c, we'll get f hat of lambda times these exponents of linear combination of these polynomials. So this gives a hint of higher degree Fourier analysis. So we are able to write this thing as this linear combination of these things which are supposed to substitute characters. Now, one of the most useful and central facts about characters in Fourier analysis is that they are orthogonal. So we need to require some kind of orthogonality if we want to use these higher degree polynomials instead of characters. So remember this decomposition theorem that we had. We decomposed f to this part, and so we can write it in this form. So let's see what is the orthogonality condition between h and this part, this structured part. So if you take any of these higher degree polynomials, omega p to this polynomial, and take its correlation with h, take its dot product, it's bounded by, so this is pretty well known and not so difficult. It's bounded by the ud plus 1 norm of h, which is at most delta. So each one of these terms, it's almost orthogonal to h when delta is small. But since the number c can depend on delta, we cannot bound this product, the product of these f with h. So we can say that each one of the terms that appear is almost orthogonal to h, but we cannot say that the whole linear combination is orthogonal.
You may want to say why it's important, why you want the correlation of h and the other part. So you have the random part and the structured part. Why do you want that correlation to be small?
Well, we want to study a correlation of f to some object, for example. Then we need, for example, f with itself even. Then it decomposes to different parts, and the dot product of this part to h will appear somewhere, or even for different functions. So when you study correlation, you cannot just ignore h.
So it's not clear that the object you correlate with will have h in it. But
No, but yeah.
Correlate that with itself.
Yes, that can be handled differently. But suppose that you have two functions and you decompose each and you are studying the correlation and you want to move just to a structured part. Then now, but fortunately there is a, again, well-known trick that can remedy this. So that gives us our second decomposition theorem. It says that take any arbitrary growth function omega and take any given function, again, f from fp to the n to minus 1, 1, so it's bounded. Then you can decompose it into three parts, the structured part and these two error parts, h1 and h2. Now again, c depends on everything, so omega, d, and delta. But the first part is again bounded. But fortunately, the part, this h1 part, its uniformity norm is bounded by this function that we picked, by omega of c. So you can make it as small as you want as a function of number of polynomials that you are using. And then we'll have this h2 error, which we can bound its L2 norm, which is a very strong bound. So it will be enough to guarantee the things that we want. So now note that if you look at the correlation of this structured part with h2, just a basic Cauchy-Schwarz shows that it's bounded by the L2 norm of H, which is delta. So these are almost orthogonal. And if you look at the correlation of structured part with H1, then so as I said, if you write the Fourier expansion of this, you can bound each term. And the number of terms that you get is p to the c. So we get this bound, which we can make it as small as we want. So we can make the structured part to be almost orthogonal to H1 and H2.
This trick appeared first in the strong form of the
Samarides. Yes.
Fisher alone and so on.
Yes, but I guess it's classical thing. It's energy increment technique. It's
Where is
maybe in ergodic theory, I don't know.
How old is it older than this?
I don't know. I don't know the references.
The oldest form of it I know is from this paper.
Okay. Yeah, I don't know the historical references. So. Now, we guaranteed the almost orthogonality of f to h1 and h2. Now, let's go inside f. So we have this expansion of f. At this point, with the second decomposition theorem, it's not clear, it's not necessarily the case that these functions, which are going to play the role of characters, are orthogonal to each other. It's not even, it might not even be the case that their average is large. So we have to fix this if we want to use them instead of characters.
Wait. So I understand you would like them to be orthogonal to each other, but why do you want the average to be large?
To be small. I want it to be almost zero. It's like a character. Yeah. Small. Yeah. So the way to fix this is through this notion of rank. So for a set of polynomials, we define the rank in the following way. So this is a definition that recently Gowers and Wolf suggested, but I'm not going to use anything from their techniques, just the definition. So we look at these averages, expected value of these things, and we see how large can they be. We want them to be small. So if lambda is 0, of course, this is 1, so we should ignore that case. And in the other case, we want to see how large it can be. And then we'll take the log and make it, take the negative of the log. So what does this rank captures? If there is one of these things such that the average is large, then the rank is small. Otherwise, it's large. So if the rank is large, then we are fine. All these averages are small, which shows that if you take the dot product of any two of these things, it also be small. So high rank will guarantee us the orthogonality. But how can we guarantee high rank? That's through the theorem of Green and Tau from a few years ago, which says that there is an increasing function r from r such that if you have a polynomial p which has degree d and some rank t, so if the rank is small, it's some constant t.
They didn't use that definition.
No, but you can use the same definition. So it's just.
So this rank is for a single polynomial?
Yes, but it's fine because this is also a single polynomial that appears here. Just if you take some fixed lambda.
You can think of this, what it was intended there as a multilinear polynomial, that the rank is a tensor rank. If the tensor rank of a polynomial is small, then this rank is smaller. But
not
the inverse is not, the connection is not clear, and that's a definition that works when you don't need to understand what the tensor rank is.
Yeah. So the theorem says that if your polynomial, if the exponential of your polynomial is large, if you take the average, or if the rank is rho, then your polynomial p is in fact, has some lower degree nature. So you can write it as a function of constant number of polynomials of lower degree. So if your polynomial has a bad average, if the average is large, you can make it, you can decompose it to polynomials of lower degree. So you can use this to obtain the last decomposition theorem, which is a very strong thing. Now, we have two parameters, omega from r to r and some r which controls the rank. They are arbitrary functions. You can decompose your function again into three parts such that, so all the previous cases hold. The infinity norm of f is bounded this is the UD plus norm is bounded by this growth function, and the L2 norm of H2 is bounded. And also the rank of your polynomial is at least R of C, some R that depends on C. And how can we obtain this, prove this theorem using this regularity theorem of Green and Tao? We obtained this decomposition theorem from the previous decomposition. We obtained this decomposition theorem from this decomposition from decomposition theorem 2. And if you find some linear combination of polynomials that has low rank, you start replacing them by lower degree polynomials. And after a while, either all of them will be polynomials of degree 1, which are just characters, or we stop because we reach some point where the rank is high.
This theorem appears also in the Gowers rule paper. That's the composition of.
Yes, this is.
Yeah, they have the same.
Yes, but I think the first place that this I saw it is in Ben Green's paper on quadratic Fourier analysis for quadratic polynomials.
This decomposition.
Yes.
Oh, that rank.
No. I mean, I'm not really using anything about that rank. You can define the rank in a different way.
But this has to be true.
Yeah, but this is a theorem from 4 years ago.
No, but this has to be true for the definition of rank you are using.
Yes.
It's not independent of the rank, this statement. So
Yes.
it has to be true for the definition of rank you are using. If you are using the Wolf-Green, the Wolf
Yeah, Gowers-Wolf.
Gowers definition, then you have to prove it for that rank, which is, I guess, easy. And then
No, but you can convert the statement to just to that thing. So I didn't prove anything. It's just Green and Tao's regularity theorem. So the way that, so let me comment on this, maybe confusion. So the way that usually we used to define rank was that rank of a polynomial is the minimum number of polynomials of lower degree, so degree d minus 1, such that you can write p as a function of them. Then you show that if the rank is high, then the average is small. So I did the opposite of this, but I didn't prove anything. It's just rephrased the statement using this new notion of rank.
so
Yeah.
that's what they do in the Gowers Wolf paper, and they derive this third decomposition theorem.
I think they handle it directly. I haven't read their paper, so it's just.
They derive
Okay.
it, yeah.
Yeah, anyway, so we have this decomposition theorem, which we.
So if you assume that p is even larger than d square or something and you use Veil, can you get better results?
P larger than d
P
square?
is larger than, let's say, the square of the degree.
Yes.
Or the cube.
So what is the parallelism?
Then you can bound all these exponential sums just using, let's say, if these pi's are linearly independent, you get the bound of d over square root p over all these exponential sums.
Uh,
And then you can just use the rank as linear as vectors.
No, but how do you define the rank again?
I'm just saying for low degree polynomial, if the field is large enough, then
Yes.
the bias cannot, the rank as you define it cannot be high. Right? That will be high. What?
No, you can. We want it to be high.
We will be high. It's the wrong. It's got a minus sign. Yeah, it can be. Yeah, the exponential
Okay.
sums are small.
Okay, the exponential sum is always a small.
Yeah.
No.
They're also at most the degree divided by square root of the field size.
Square to the- Oh, okay, but the dependence is.
As long as it's not a fixed constant. As long as it's not.
Okay. Okay, so then we can discuss later. Not sure. So let me finally say what this Gowers-Wolf complex is. So consider a system of linear forms L, which is L1 to Lm, and let's look at this expected value that we defined before, T sub L of F. Now, if the system has Gowers-Wolf complexity d plus 1, then if you use a strong enough decomposition using the previous decomposition with strong enough parameters, then TL of F will be approximately the same as TL of this structured part. So that's exactly what this Gowers-Wolf complexity is. So it allows us to remove these two error terms when we are looking at these averages. So that's the definition of Gowers-Wolff, and then the question is can we characterize these things, which they did. Gowers and Wolff, they characterized these systems. Now consider a system of Gowers-Wolff complexity d plus 1. So we can remove these error parts, h1 and h2. So we want to be able to analyze these averages, TL of this structured part. Currently, with the orthogonality that we proved in the decomposition theorem, we can easily analyze these kind of things, omega p to this linear combination of polynomials, which is basically if lambda is 0, then of course the power is 0, so this expected value is 1. If it is not 0, then this expected value is very small. So it's either very small or it's 1. We can understand these things. But let's see, what do we need to understand if we want to look at these averages for the linear forms. So let G be this structured part. G of x is f of that polynomial. Now let's look at this product of G on different linear forms. Then if you look at if you substitute the Fourier expansion of G, which is just these f hats of lambda, these linear combinations, then, and you expand this product to get these sums, the sum over all these vectors, lambda 1 to lambda n, and then these things. But look what happens in the power. We get this linear combination of polynomials which are applied to linear forms. So to be able to analyze this, we need to understand these kind of averages, which are a bit different from what we had before. And it's not clear how to analyze them in the first place.
So what is the random variable in
This
this
is
just
x, yeah, which is a k tuple of vector points picked uniformly at random.
Did you define the Gowers-Wolff complexity?
Yes. So it just tells us that you can ignore the high part. I didn't tell you about the characterization. It's just definition. It says that this is approximately the same as the same product for f when you take the average. Okay, so we need to understand these things.
Well, I mean, it's the degree of the polynomials that, for which you can do this.
The Gowers-Wolff complexity of a system of
Linear form is the largest, is the smallest d such that you can apply the decomposition theorem with degree d and remove the error part. So you can remove the ud plus 1, the uniformity of degree d plus 1 from the error term. So your polynomials will be, you can make sure that the polynomials have a degree at most d when you approximate your function. Okay, so we had this when the rank is high. We had this almost orthogonality things. Now, the first lemma, which is, again, a very central part of the proof, is the following, that we want to prove something similar for these linear forms. So the lemma says that if your rank is high enough, if you look at this polynomial in these multivariables, which each one was a vector, so you have these linear forms here, then one of the following two cases hold. Either you have complete cancellation, and this is the 0 polynomial, so this p omega is 0, and then, of course, this average will be 1, or the average is small. So something similar to this. Either you have complete cancellation, you get 1, or it's fine, we get something very small.
Who is L? This is your paper?
Yeah, this is the algorithm. Yeah, this is joined with Shachar Lovett. I didn't mention it. And our second lemma is the following. So what this lemma tells us that we can move now to algebraic setting if we want to understand this kind of exponential sums. Because so either we have this polynomial which is completely 0, or this sum is 0. This sum is this average is almost 0. So we need to understand when we have complete cancellation and this polynomial is identically 0. And our second lemma says the following. Consider a sequence of positive integer, which is a degree sequence for us. Some linear forms L1 to Lm, and some constant lambda ij in Fp. Then one of the following two cases holds. Every linearly independent homogeneous polynomials P1 to Pk of degrees D1 to Dk. So you have, if you take any set of polynomials, which are P1 is of degree D1, P2 of degree D2, and so on, and they have to be linearly independent homogeneous. This sum is 0. So either we are in this regime or here, that this sum is not 0 for any such set of polynomials. So the lemma says that this sum being 0 is just a property of degrees of these polynomials if we restrict to linearly independent and homogeneous case, and not the particular choice of polynomials. So it's not important what are your polynomials. It's just the important thing is that what are their degrees. So this is the first lemma. Now, when we sure.
What's an example of the first case?
For example, if you have if you use no, not Gowers-Wolff, just the uniformity norm, the linear form that come from the uniformity norms, and say uniformity norm of degree d plus 1. And if you use a polynomial of degree d, then you'll have complete cancellation. So that's the reason all these lambda ij's are 1. That's the reason that polynomials of degree d, they have uniformity norm 1. Because you get complete cancellation. Yeah. Any questions? So in order to prove the theorem about the testing, we need to be able to also deal with non-homogeneous polynomials. Because we don't want to distinguish between a high-rank polynomial, high-rank homogeneous, say, quadratic polynomial with a high-rank non-homogeneous quadratic polynomial. Now, consider a polynomial p and some number L. Let p to this L in bracket denote the part of the polynomial which is homogeneous of degree L. So it's just the monomials that have degree exact L. We remove all the other parts. Then our third lemma says the following. Again, now take a system of linear forms which is homogeneous. So all these linear forms, they start with constant 1. So the first variable, it has coefficient 1 in all these linear forms. And again, these constants lambda ij. Let di be the degree of polynomial pi. And let's look at these pi to di. So we remove all the lower monomials of lower degree. Then this is 0 if and only if this is 0. So again, this linear combination being 0 is equivalent that just the higher degree part of the polynomials, the highest part of the polynomial, which are the monomials of degree exactly di, gives us 0. So if your linear system is homogeneous, then again, it's the same thing. We don't need to distinguish between homogeneous polynomials and non-homogeneous polynomials. We have the equivalence.
So, maybe I don't understand. Homogeneous refers to what now? The
Linear.
The presence of the first variable in all the
Yes.
linear form.
Yes, with coefficient with same coefficient. So this doesn't hold if your system is not homogeneous. It only holds for homogeneous systems of linear forms. But in testing, all the linear forms that we use are homogeneous. So it's fine when we want to apply this. Now, what is the corollary to these lemmas? Consider a system of a homogeneous system of linear forms L. And let's look at two sequence of polynomials which are of sufficiently high rank, and they have the same degree sequence. So degree of pi is the same as degree of qi. Now, let's look at this average. So when you look at the average of this product, as I said, it's just for some of these higher degree characters, you get this becomes 0 and you get 1. For the other ones, it becomes very small and you can ignore them. But if your polynomials have the same degree and the rank is high, it doesn't matter if you use pi's here or qi's here. You get the same average. So if you look at the average with polynomials p1 to pc, you'll get almost the same average as you use polynomials q1 to qc. So when you take this average with respect to L, it cannot distinguish that which set of polynomials you're using. It's just, the degrees are only important.
You just have to count the number of times it is 0. That's the only important.
Yes, with the coefficients.
So it's just the 0 term.
It's not the 0 terms. For some lambdas, you will get a 0 where you don't expect it. Right? You will get constellation where you don't expect it. But it's only these contributions that matter. All the others don't matter because the rank is high. So even component-wise, the value of this exponential sum is small. You can write it's much smaller than the number.
Yes, yes. You can make it as small as you want.
Yeah. But it's just the number. You just want to know how many times you get complete cancellation.
Yes. You want to know when you get complete cancellation, not how many times.
Oh, yeah.
Yeah, because it depends on the function f.
Yeah, because that weights.
Yeah.
Well.
Okay.
So the general claim here that for a system of linear forms of Gowers-Wolff complexity D, take a function of things of degree d minus 1 or
D. Okay.
D, then you can replace it with any other function.
Yes, if your rank is.
It's insensitive to functions of degree, to shifts by functions of degree D.
To any, if you.
Change of.
Yes, to change of the functions. Okay. So, right, I'll move to the proof now. We can take. No, I'm fine if people. Yeah. So let's continue. So these are the tools that we're going to use. Now let's go to the proof. So let me remind you of the definition. We call an invariant family correlation testable if you have this homogeneous system of linear forms for every epsilon, such that if you look at these averages for uniform and non-uniform, you get two disjoint sets, two sets whose with disjoint closures. And we had this Gowers-Wolff condition. And the theorem that we are going to prove is that if your set has a small uniformity with respect to D, if and only if it has a small uniformity with some K Gowers. Now, so let me tell you about the steps of the proof. Consider some homogeneous system of linear forms, L1 to LT, which comes from the test, of course. Consider some G inside our set Dn. Suppose that G has large correlation with the exponent of a polynomial of degree K and high rank. So you have this polynomial of degree K inside G somewhere. There's some correlation. Inside Gn, which is inside Dn. Now consider an arbitrary function f, which correlates with some other polynomial of, again, high rank and degree K. We want to show that f is non-uniform with respect to our set Dn. So because the linear forms are of low Gowers-Wolff complexity, you can approximate f with this function of polynomials of degree at most at D that we had. Now, we can assume that since f correlates with a polynomial of high rank and degree K, one of the terms that after writing the Fourier expansion, one of the terms must be of degree exactly K with some large coefficient. And since we are not restricting to homogeneous case, we can assume that that's Q1 and that f correlates with omega p to Q1. So this is of degree K, and if if you just look at the coefficient that corresponds just to this one, it's large.
So you'll replace it with G.
Yes, now, yeah, we want to do something similar. Now, we pick some other polynomials, q2 prime to qc prime, with the same degrees as q2 and qc that have nothing to do with G. So, for example, we can pick them completely at random. Then we look at this thing, f, which we use p, which comes from G, and we use these things here. Then this correlates with G because of this part p, because it appears in both G and f. And these are, they are completely orthogonal to G, so they don't cause any trouble for us. Now, we have to accept this function because it correlates with G. But what, so our test has to accept this because it correlates with G. But if you look at TIs, if you look at these averages TIs, only degrees were important. So if we are accepting this, we have to also accept f of q1 to qc because they have the same degree sequence. So we are accepting f. So this tells us that our test accepts f if it correlates with a high rank degree k. If there is some G which correlates with a high rank degree k polynomial. Okay, so this is, and in the last step we use the fact that these are non-homogeneous. These are homogeneous systems of linear forms that we can substitute any set of polynomials with any other one. Okay, so if there is no question about this, I'll move to the next part of it. Okay, so far we showed the following. If there is some G that correlates with a high rank degree k, we are accepting every f that correlates with a high rank degree k. But this high rank is a problem here. It doesn't give, so we are not done with our theorem yet, because we want to show that we are accepting any polynomial, any function which has large uniformity norm. But this, one of the reasons that can this happen is because f correlates with a high rank degree k. But it can also happen if f correlates with a high rank degree at most k, with something with lower degree. So we are not done yet, and that's the second part of the proof.
You put one direction of the implication.
No, I haven't proved actually. Well, one direction is easy, but this is half of one of the directions. So I want to show the.
Just separate. So okay, I understand. You put it this direction only in the case that the correlation is with high rank.
High rank, yeah. Yeah, I need to prove it for lower ranks. So how does the proof goes for the second part? Consider some systems of linear forms L1 to Lk and some degree r which is less than k. Now, to prove the second part, I'll show that there are functions f and h such that f correlates with a high rank degree k, so we have to accept f. H correlates only with high rank degree r polynomials. So h is something which is consists of only polynomials of degree r, high rank polynomials of degree r. So there is no other structures inside that. And that TLI of f is the same as TLI of h. So since we are accepting f, we have to accept h. So h must correlate with some element inside G. And h has only polynomials of degree r. So we have to accept everything that has polynomial of degree r. So the test cannot distinguish between f and h. It has to accept h. And then there is some G in the end which correlates with h. So it correlates with something of degree r. And then the previous step shows that we have to accept everything that correlates with some high rank degree r. Okay, now how to prove this? So I'll define two notions by examples. One is I call a system of linear forms disconnected if you have this situation that if you look at the expected value, it decomposes to two different expected values. So for example, here, expected of f of x times f of y, x and y are independent random variables is this. And the second is that you can have isomorphic systems of linear forms. The only important thing is the linear structure in the linear form. So you can state them differently. For example, if you look at this expected value, x and x plus y, it's the same as the expected value of x and y. So in this case, I call these two systems of linear form isomorphic. And to prove the second part, we need the following theorem. Not necessarily need, but that's the way that we prove it, that if you have these connected and non-isomorphic systems of linear forms, and if you let n to be sufficiently large, then if you look at all these functions from fp to the n to 0, 1, and if you look at their profile with these linear forms, then you get a set of points. And I want to show that this has non-empty interior. So there is at least one ball where you can attain all the points by looking at these averages. So when we were trying to prove this, it seemed like a very easy statement to prove. Then we found this paper of Erdős, Lovett, and Spencer where they proved a similar theorem for graphs. And that's not very easy. And even worse, the proof completely falls apart when you try to do it for linear form. So the proof that I'm going to sketch for this is completely different. So if you look at, if you have non-isomorphic connected graphs, similar to here, and if you look at these averages, homomorphism densities, T sub H1 to HK, these are the graphs for some different graphs, you get again a set, and they prove that it has non-empty interior. So the average, the subgraph density here is replaced by this linear pattern density.
So what would be the, so this is a generalization of the theorem?
I think, yeah, it's possible to derive that.
The linear system are just the linear equations?
Yeah, probably you can take, yeah, x plus xi plus xj if ij is an edge, then yeah, I think it's possible to derive the result from this.
So, but just a bit, so connected and non-isomorphic means that there are correlations. So, I mean, you didn't define.
Yeah, exactly what it means.
Really define what connected is.
Connected means that you cannot decompose your set of linear forms into two sets such that their span doesn't intersect. So it intersects only at 0. And non-isomorphic means that there is no invertible linear combination from the span of this set to the span of that set. So it's a linear algebraic. Now, how do we prove this? It's actually pretty difficult. I don't know any simple proof to this. So we look at these functions, which I denote by f rho of L. So you take a system of linear forms. Then this function is defined the following way. It maps every x to the following derivative. I add f plus the direct mass weight or mass function on x. So that's just 1 on x. And add the multiple of t to f. So this is a function, and I take its derivative with respect to t. Now, we have to find some functions f such that these are linearly independent. If we can do this, we are done, because we can move in different directions, and then the interior will be non-empty. Now,
Is there an intuition for this function now? This f?
it's a function, again, from fp to the n.
Yeah, but
It's a generalization of, say, convolution. It's similar to one flag algebra thing, Rasborov's one flag algebra for graphs. Two flag. Yeah. Yeah, I mean, the intuition, I mean, maybe for me at least it was coming from flag algebras, Rasborov's flag algebra. Now, if they are not always dependent, if they are always dependent, we want to show that there is some function f such that these are independent. But if this is not the case, then they must be also dependent as polynomials in these variables. So if you look at f as some variables which gives the value of f on different points, then these are polynomials on these. Each coordinate, these are vectors where every coordinate is a polynomial in these variables. So they are dependent. So you can find some polynomials, p1 to pm, which are of these variables, f of x, where x is there. And you have this complete cancellation. This is the zero vector. Now,
The polynomials are of some degree. I mean, they are
Ye-
polynomials over the values of the function.
Yes.
Over the whole field of all the vector space. So what is there a restriction on the?
yeah, we can bound the degree. So
bound in terms of what?
So we can bound the degree of these polynomials in terms of these size of these linear forms, linear systems that we are using, and k. So I'll continue the proof from here. So we can find these polynomials such that you have complete cancellation here. So these functions are dependent over this over these polynomials. Now, we can make sure that the degree of these polynomials doesn't depend on n. It just depends on the size of these linear forms that we are using and k. Now, we symmetrize these polynomials. Since this function has some symmetric properties, we can use different symmetries and take the average. You'll find some other polynomials which are actually linear combination of these functions, t L primes for some linear systems L primes. Then from this, it's easy to get a contradiction with the assumption that the original linear forms were non-isomorphic. So after we add these polynomials, we just take different averages, and these things become these averages, this TL kind of thing, averages over linear forms, and then non-isomorphism will help us to get a contradiction. Okay, so that's the, and once you had this non-empty interior, it's easy to construct the functions g and h that we wanted with this property, because it gives us a very dense thing for a constant n. And I'm not going to tell how to construct it, but this part is very easy once you have that. Okay. So this was the theorem that we proved. That was the proof. And let me just go to open question part. So the main thing that remains open is the low characteristic case. So in the low characteristic case, there are some things which are called phase polynomials, which substitute the polynomials that we have here, these exponentials of polynomials. First of all, I don't know any satisfactory regularization for these low characteristic fields. So such that it satisfies this strong orthogonality form that we want, that either you have complete cancellation or you get some averages which are very small over linear form. In fact, if you can prove such a regularity thing, it will prove the inverse theorem for low characteristic polynomial. Currently, there is only a partial result there. So another problem, which is actually one of the motivation which started this thing, but we couldn't solve it, is the following. So this is a conjecture by Berger, Santana, and Ziegler, which says that if you're which basically says that there is a correlation test for cubic phase polynomials in fp to the n. And so it says that for the U4 norm, if the U4 norm is large, then your function correlates with a cubic phase polynomial. So that gives a test for this, and similar to the way that we had tests for polynomials here. But even if you assume this conjecture and assume that you have this regularity theorem, we don't know the following. Is there a correlation test for just cubic polynomials in fp to the n? So we have a function from fp to the n to minus 1, 1. We want to see if it correlates with an exponent of a cubic polynomial. I mean, there are no conjectures that I can assume and solve this. So our techniques fail here. Actually, we have some candidates which might be tests, but probably they are not. But we cannot show under any conjectures that they are not tests for polynomials of degree 3. Yeah, so I have to stop.